I finally have the X-axis of the grinder moving smoothly between the limit switches under software control. It was not a smooth path to get here, but we did get here. Welcome back to Cloud 42. I'm James. We are back on the surface grinder automation project today. In previous videos, we built and installed the servo motor drives for all 3 axes, though you'll remember that the X-axis wasn't moving smoothly at all. We'll deal with that shortly. Last time, we designed and 3D printed a couple of sets of limit switch mounts to control the table traverse, and today, we're going to try to put it all together and make it actually move under software control. We should be ready to test. I've got the servo motor here connected via a belt drive to the input shaft on the grinder. That shaft drives a spool that then drives the cable wound around it to drive the table back and forth. Everything is running nice and smooth. You can hear the phase converter because I've got the lubricant pump on in the grinder. We've got our limit switches here that we made in the previous video. And we've got the cam set on the table, not too close to the end so we don't risk crashing it, but far enough that the table should be able to get up to speed. Then those cables come over to the bench here where I've got them connected to the ClearCore controller. We've got the 2 limit switches left and right hooked up to inputs 2 and 3 and the motor connected to motor 0. And then on input 1, I've also connected an emergency stop switch. And for now, I'm just going to use this to turn the motors on, let it run, and hit it to turn it off. Got a bench power supply to provide the 24 volts to run the ClearCore. And if I power that up, you can see it's got all kinds of nice bright blinky lights. One of the things I really like about this as opposed to an Arduino is it has these lights down on the connectors that show you the status of the inputs. So I'm pressing the limit switches with my right hand and you can see the lights are blinking. That's just great for debugging. I put together some very simple firmware for the ClearCore just to do some initial testing. You can see here I'm including the ClearCore libraries published by Technic, and then I've got some definitions up here at the top to do the basic math because the library wants movement in steps, but I really want to think about it in RPM for this case. And it looks like I actually made a mistake here. I've got 1,000 steps per revolution. That's wrong. The motor's set to 800. And then the rest of this is just about calculating the RPM and whether left and right is positive or negative. To start, I'm going to start very slow with 100 RPM and 5,000 RPM per second acceleration. I think that's going to be safe. And then I've got some definitions here just to put some friendly names on the motor connectors. Now, when I did this initially, the code looked like this without the pointer syntax notation. This is C++, but because they used initial caps on all of the object names, and because I'm working in a variant here of Visual Studio, my brain just went back to my C# days, and I thought I was dealing with a reference language, and it took me a while to figure out I was doing a copy assignment when I really needed to be setting up pointers. Anyway, this whole thing is a state machine. I've got 2 states. We're either moving right or we're moving left. So after we do the initial setup on the motors and the inputs, there's just a loop here that runs through this continuously. If the E stop is pressed, we stop everything. If the left and right limit switches are clicked at the same time, we stop everything. And then after that, we're just going in an infinite loop. If the left limit is hit, we move right. If the right limit is hit, we move left. And then we go through and actually command the motor to either move right or move left. Now, I'm going to be calling these over and over and over again, but the underlying library is going to keep track of the fact that I'm commanding it to do the thing it was already doing, and it should just work. And then I've got a default case down here to just stop the motor. There is no other case besides left and right, but just in case I change something in the future and I make a mistake with this, I just want everything to stop. So consider that paranoia. Then I'll click the button here, it will build and then flash into the controller and we get a nice little light show, which is kind of fun. And that's it. The ClearCore is programmed and we should be ready to give this thing a test run. I'm going to start out nice and slow at 100 RPM and 1000 RPM per second acceleration. We'll just program this into the ClearCore, hit the button and see what happens. And that is nice and tame. The point of going this slow on the first run is to make sure I have lots of time to hit the e-stop switch if something goes wrong. But this looks pretty good. I did some bench testing, so I was pretty sure it was going to work. Let's go ahead and bump it up to 200 RPM and see what that looks like. Program that into the clear core. And that seems nice and smooth. Now you note that it is overrunning the switches just a little bit further because we haven't increased the acceleration yet. We'll do that in a little bit. But that looks okay. Let's go ahead and bump it up to 300 RPM. I want to take baby steps here because I don't really know when things are going to go wrong, and I would like them to not go wrong badly when they do. That looks pretty good. We are overrunning the cams just a little bit further. Let's try 400 RPM. That's still nice and smooth because we haven't bumped up the acceleration rate, but you can see it's significantly overrunning those cams. So we're going to need to bump up the acceleration so we can get it stopped and turned around faster. Let's go to 2000 RPM per second and see what that looks like. That's quicker. It's still pretty smooth. I can live with that. Let's try 3000. That's a little snappier. I like that. I think we're going to need to go further because I'm planning on going to even higher speeds. So let's go ahead and bump this up to 5000 and see what happens. Okay, it's difficult to see in the video, but I'm just starting to be able to see a little bit of bounce at the end when it turns around. So it's hitting the end, and then on the way back, it's kind of jiggling and bouncing. It's really hard to see here, but it's something that I can definitely feel. So at 5,000 RPM per second acceleration, we are starting to hit the limit of what the servo can control, at least with the default settings. Let's go ahead and bump this up a little bit further. Let's go to 600 RPM and maybe 6,000 RPM per second. That's pretty snappy. We are still overrunning the cams a little bit further than I would like. And you can kind of see the belt reacting a little bit. There's a little bit of jiggle as we go past center rather than it running nice and smooth. So you can just visually see a little bit of the oscillation occurring there. And you can definitely see it when I stop in the middle of the move. There's more going to the right than there is going to the left. That's because the spool is off center on the cable. There's more cable on one side than the other. But that jiggling motion, that's occurring at the turnaround point, whether you can see it or not. You can just see it better when we stop in the middle. Let's bump it up to 8,000, see if we can make this really evident. I like how snappy that is on the turnaround, but that's definitely not behaving itself. You can see the trapezoidal move. This is the blue is velocity and the red is the position error. So you can see it's starting to have quite a bit of oscillation and show quite a bit of position error. Especially if I'm stopping and starting it, you can see the servo just completely losing control. Those big spikes in the position error are a problem. So what's going wrong here? The simple answer is that the mechanical system is springy. The table on this grinder is driven by a wire rope wrapped around a drum on the input shaft, and with the mass of the table and the amount of force being applied to move it, that wire rope acts just like a spring. When the servo applies force to move the table in one direction, it stretches, and when the servo applies force in the opposite direction to stop the table and reverse it, that stretch rebounds and the other side of the cable stretches. Now the servo can't actually see this. It doesn't see the table movement. It can only see the motion of its own shaft. So it can't tell exactly what the table is doing to counter it, but it can see the forces reflected back to it as the inertia of the table acts through that wire rope spring. There's energy sloshing back and forth in the system, and that's the reason why the servo is getting confused and struggling. I did run the auto-tuning algorithm on the servo so it could learn how the axis behaves and set its control parameters. And while that worked great on the Y and the Z axes, the springiness of the X axis confused it. So I contacted Technic, and someone from their applications team connected to my computer remotely and manually tuned the motor. That got it working better than the auto tuner, but as you saw, it's still struggling. They suggested that I might want to try the enhanced version of the motor, which has their Regressive Auto Spline smoothing algorithm, and spoiler alert, yeah, it helps a lot. Unfortunately, this does require replacing the motor with a new one. Fortunately, they have a 90-day return policy on the first motor that I bought. Unfortunately, I was 2 days outside of that window. Fortunately, I can find something to do with an extra Clearpath servo. So what exactly is this Regressive Auto Spline or RAS thing? Well, if we look at the Clearpath motor user manual and go all the way down to page 199, it discusses a couple of vibration reduction and resonance suppression features. The Regressive Auto Spline, which we're talking about here, and there's another technology called G-stop that's kind of related but isn't relevant for what we're talking about here. So this is a vibration and resonance suppression feature. So the idea is to help produce, they say, smooth motion, reduce machine vibration, improve settling time, and decrease audible noise. That sounds great. That is exactly what I want. So it says RAS is a jerk limiting and jerk derivative limiting feature. Well, what does that mean? There's a really great article out here on Wikipedia about jerk. Turns out jerk is not just an interpersonal phenomenon, it's also a physics phenomenon. And if you remember your high school physics or high school calculus, you'll know that if you take the function for the position of an object and take the derivative of that, you get a function for the velocity or the speed of the object. If you take the derivative of velocity, you get the acceleration of that object. And that's as far as we generally go with high school physics or any high school math. But it turns out you can take that further. So velocity is the rate of change of position over time. Acceleration is the rate of change in velocity. Well, jerk is the rate of change in acceleration. And if you take the derivative of jerk, you get the jounce, which is the rate of change of the rate of change of acceleration. Now, why do we care about this? Well, there's a whole bunch of stuff in here and a whole bunch of math, but as a practical matter, what you're trying to do is limit how fast the acceleration comes on and goes away. So if you think about driving in your car, when you press the accelerator down, you are adding power and creating a force that leads to an acceleration of your vehicle. You don't want to do that suddenly. You don't want to slam the pedal to the floor, and when you get to the speed limit, you don't want to lift suddenly and throw your passengers forward. You want to ease into the acceleration and ease out when you reach your desired velocity. The same thing, by the way, occurs in track or road design, where you're coming in a straight line and you need to enter a round curve. You don't want that line to come tangent to the curve because you would suddenly have to snap the wheel to the side and it would throw your passengers around. Instead, you have a gradual transition. And what this is doing is limiting the jerk of that horizontal acceleration. So if we go back to the Clearpath manual, this is exactly what they show here. So this is a velocity versus time curve showing what's commonly called a trap move or a trapezoidal move, where the system is at some velocity, maybe 0, and you start accelerating to accelerate up to a desired speed, and then you decelerate back down to, let's call it 0. And in a trapezoidal move, that acceleration starts suddenly and stops suddenly. So the force that's causing that acceleration appears and then vanishes in an instant. So you have this moment of instantaneous change of acceleration. And what jerk limiting or the RAS feature is doing is it's rounding the corners of that trapezoid. So it is changing the instantaneous change of acceleration into a more gradual change of acceleration. And again, they don't give the details. They just say something about fitting a fourth order polynomial spline to the motion. That sounds great. The details don't really matter to us. What's happening is it's just rounding the corners of this trapezoid so that it's not bringing on the acceleration suddenly. It's happening more gradually, giving the machine, which you always have to think of everything being flexible, it gives it time for it to react to that rather than just hitting it with a hammer and causing it to move suddenly. Now, if you want to know all the details about how all the math works there is a video that they've published out on YouTube. I'll put a link to this down in the description, and they go through it in a lot of detail. If you're interested in the topic, I definitely recommend checking that out. Now, the one thing that you do have to be aware of, though, is that because the motor is the last technical item in the chain, it's the last thing to know about what you want to do. It doesn't know that you're going to accelerate. It doesn't know that you're going to stop acceleration until it actually receives those commands. So if it's going to smooth out these curves, it's going to introduce a delay. So if you're sending commands to make a trapezoidal move, it can't move suddenly and follow that path. It has to lag behind it a little bit, because if it's going to smooth out that curve, it has to have time to accelerate. So it's necessarily going to fall slightly behind. And how far it falls behind depends on the setting. If you have it set to 0 milliseconds, it's going to follow the trap curve. If you have it set to 99 milliseconds, it's going to fall a little bit behind. If you have it set to 197, it's going to fall even further behind. And you could, in theory, with a motion controller that implements this, start early so you stay closer to this curve, but you can't do that in the motor because the motor doesn't know in advance that you're going to make the move. So this is the main trade-off, is as you turn this value up, you get smoother motion, but at the same time, you introduce a little bit of a delay. Though technically, because there is less vibration, the settling time might be faster, so when you're designing your machine, you might actually be able to move on to the next move sooner. Now, as a practical matter, we do need to get a different motor to enable this. This is the motor that I bought originally. This is the regular version of the NEMA 34 Clearpath. And I chose this particular model of motor based on the peak and continuous torque and the torque to speed curves. I still think this is about the right motor for this application, but there are two versions available. There's an enhanced version and a regular version. I got the regular version. The main difference is the regular version has a maximum resolution of 800 steps per revolution. If you need more than that, the enhanced will go up to 6,400 steps per revolution. And the other is the RAS or jerk limiting settings that are available. There's a little bit of RAS available on the regular motor, but if you want to get up into the range that we're going to need, you have to buy the enhanced version. So for this particular motor in the US right now, it's $371 for the regular version, and if we select the enhanced version, it's $428. So you are paying a premium for those features for essentially the same basic motor, but with the additional resolution and the additional RAS settings. Before we turn up the RAS value, let's run this again with the settings that we had before. That's 600 RPM and 6,000 RPM per second acceleration, and take a look at the scopes. Now the blue trace here on the scope is the velocity. You can see it's close to a trapezoidal motion curve, and the red trace is the position error. If I switch that over now, so the red trace is showing the torque, you can see the motor oscillating in its torque output, trying to fight that vibration that it's seeing feeding back through the springy cable from the table. And you can really see it fighting to try to bring it to a stop. Now the RAS value is currently set to 16 milliseconds. That's the maximum you can set the non-enhanced motor to, but we can set it higher on the enhanced version of the motor. We're going to dial it up here to 197 milliseconds, which is kind of what I've determined is about optimal for this setup. And you can see two things immediately. First, the corners of that trapezoid are rounded over. And second, the torque oscillation is gone. We just see a spike in the torque when the table actually changes direction, and then the continuous torque while the table is moving is much lower, and you don't see those big oscillations. Overall, the motion is much, much smoother. And if you look at the belt, you don't see the belt flapping around because those torque oscillations are not there. And switching back to the position error on the graph, you can see the position error is much smaller and it reaches steady state much more quickly. And we don't see any of the oscillation or bouncing on the stop either. That is a huge improvement. Now that we've tamed the system down, we should be able to turn the acceleration up higher. So this is 6,000 RPM. Let's go ahead and bump it up to 10,000 RPM per second acceleration and see what that looks like. It's a little quicker on the turnaround, but it seems to be just as smooth. And we're still not seeing any bouncing on the stop. Let's bump it up to 15,000 RPM per second acceleration. That's even quicker. It's traveling not as deep into the stop as it was. Because of the delay from the RAS, it was traveling a little deeper into the stops than what we were seeing before, but turning up the acceleration will help to counter that. Looking at the torque curve here, you can see that there is a little bit of oscillation. There's a little bit of energy being fed back to the motor, but it's nowhere near what it was before. That still looks pretty smooth. Let's turn it up some more. That was 15,000 RPM per second acceleration. Let's turn it up to 20,000 RPM per second. And that still looks pretty good. This is 4 times, or almost 4 times the acceleration that we had without the RAS value at 197 milliseconds. Yep, and it's still not bouncing on the stop. So even at the higher acceleration, that is still running a lot more smoothly. How high can we take it? Let's try 25,000 RPM per second acceleration. And that's even quicker, but the turnarounds seem pretty smooth. We are starting to see a little bit more oscillation in the torque curve there. And you can see the rounded corner on the trapezoid is a little bit sharper. It's still rounded, but it's sharper because the acceleration is so much higher. But the position error still looks pretty good. I think this is probably about as far as I want to push it. I think that's a quick enough turnaround. That looks to be working okay to me. Let's go ahead and adjust those cams and see if we can get this to travel all the way out to the ends of the chuck so that we could actually dress the entire 18 inches of the chuck with the, about 19.5 inches of travel of the machine. Now, I've been running this before with some different settings, and I've got some little marks there for the maximum position I could put those cams out to without crashing into the end of travel. But I'm going to sneak up on this slowly. I'm kind of looking at the end of the guards there and trying to understand where I am. That's running nice and smooth. I think we can go all the way out to those marks. When I was testing before, I had the steps per revolution on the motor set to 1,000 instead of the correct 800, so I just want to be careful here and make sure I don't hit the end. So I believe that is the full travel. We're traveling more than the 18 inches of the chuck. We're getting within a millimeter or 2 of the end of travel of the table. And that looks great. I think that's probably faster than I would have been able to crank this by hand. That looks good. I think I'm going to stop tuning here. I think these settings will work just fine for what I want to do. Now, there is one thing that I would like to try. Let's go ahead and lower the RAS value now that we have the acceleration turned up and just see what happens. I'm just going to lower it to 130 milliseconds. I'm not going to turn it completely off, but just lowering it, let's see how the machine responds. Yeah, that's not good. Oh, look at the position error. Yeah, that's just all over the place. And that little beep and flash you saw there was the motor torque saturating. So it reached the maximum torque output and had to reduce power. So yeah, that's not going to work. It would not be able to run at these accelerations without that high RAS value. So we'll set it back to 197 and we'll leave it there for now. Yeah, looking at that position error, I am really happy with that. It's so much better than what I was seeing before. I think this is going to be totally usable for actual grinding. And I don't think that that measured torque oscillation is going to be too big of a problem. We'll see if it shows up in the grinding finish, but I think this is probably going to be just fine. And it looks like the absolute maximum peak on the torque there is still well under 50%, maybe 35, 40%. So I think we've got plenty of margin left on the motor. Now that's more like what I had in mind when I started this project. There are always little twists and turns with large development projects like this. I was pretty discouraged when I saw how the table was moving initially, but I stayed with the problem and eventually found a solution. And as usual, I learned a few things along the way. There's still a long way to go on this project, but it feels good to finally have something, anything, actually running end to end. If you enjoyed this video, give it a thumbs up, feel free to subscribe, and maybe think about supporting the channel over on Patreon. Patrons can download files and drawings for all of my projects and get access to the Cloud42 discourse forums for a little peek behind the scenes. I'll put a link in the description. Thank you for watching.